tell us a little bit what he has been doing in the past, what he's interested on, and to establish connection between the audience and him. So please listen carefully and try to come up with good collaboration strategies.
Thanks.
Okay.
Okay. Maybe. Okay. So hi to everyone. Very happy to be here. And I came here 2 weeks back, as Raul was saying, to start a postdoctoral fellowship within the Maria de Mezzo program. And so I will be here for the entire 2026. And so if I understood well, the meaning of this presentation is to give a sort of overview of some of the things, some of the research activity that I have done in the past, some of the things that I would like to do with the time I have here, and this could be a sort of starting point to have some future discussion with those of you who might be interested in some of the things that I will say, and so then we can build new collaborations and things like. Okay. So let me start. Okay. Yes, this works. So basically, just to summarize the kind of research activity that I have done both during my PhD and my first postdoc. Somehow it's at the interface between statistical physics and inference problems in high dimensions. Okay, but from an algorithmic point of view, which is more connected to the first part of this talk. Let's see if this works. Yes. Which is about energy-based models at the interface between statistical physics and artificial intelligence. And also there will be a more theoretical part, which is more like within the statistical physics community of spin glasses, which deals with the planted inference problems in a sort of cooperative learning setup. Okay. So first, just to give an introduction about my background. So I did my PhD. Actually, I did all my career at Polytechnic of Torino, so in the northwest part of Italy. Actually, I did my master in physics of complex systems. I don't know if you know, so there's this master program which is shared between the Polytechnic of Torino, then SISA and ICTP in Trieste, and then we also spent 1 year, one semester in France, in Paris. Then I came back for the PhD at Polytechnic of Torino. I worked with Alfredo Braunstein and Luca Dall'Asta. Maybe some of you know them, I don't know. So during that, basically, just to give a brief overview of my past research activity, during my PhD, I mostly worked on some MIMFIL-like approximation schemes to compute observables in probabilistic graphical models of, in this case, of binary spins on sparse but loopy graph topologies. And in particular, we worked on how to extend some of these techniques, in particular the class of message passing algorithms in such a way to take into account in an effective way for the effect of loops in the starting graph, okay, if you have loops. This was somehow a bit more than half of my PhD. Then the last year of the PhD coincided with the first wave of the pandemic. So I mean, we did also some work which was a bit more applied, and in particular in the context of epidemic inference in spreading dynamics on graphs, with the main application that in this case was sort of to design online epidemic mitigation protocols. So the idea is that you can, based on some information which might come from the knowledge of the graph of interactions between individuals and some information which might come about the test results that people can undertake, you can run some Bayesian inference scheme, and you can compute the probability at each time of the epidemic dynamics which is going on, and you can compute the probability that each individual is infected or not alongside the dynamics. And based on that, in principle, you can quarantine the individuals with the highest risk of being infected. So this was somehow the last part of my PhD. There's also, I mean, we did also some subsequent works, basically between my PhD and my postdoc. So then I moved to Spain. I came to Spain, but I went to University Complutense of Madrid for a postdoc, almost for 3 years. I worked with Aurélien Desel and Beatrice Swan. I don't know if you know them, but okay. I worked, in this case, I worked a bit more at the interface between statistical physics and artificial intelligence. And this will be basically the 2 topics that I will discuss in this talk. Okay, so one is about, in a very generic way, about energy-based models, and we did some theoretical works on this. And then also some theoretical analysis of neural network models, also in the context of associative memory models, like the Hopfield one, using disordered system theory. So just as a disclaimer, so the kind of research activity that I have done so far does not focus on a specific problem, somehow on a specific physics problem in itself, but it's rather on how to, I mean, it's more of a sort of interdisciplinary approach, because we always work on how to how to develop algorithms and tools which you can use in a variety of contexts. So this part of the talk will be about energy-based models, and the basic idea is how to encode, how to model complex sets of data using statistical physics tools, and how to extract, in particular, effective interactions from data. Okay? Of course, if you have any questions, please feel free to interrupt me at any time. From an artificial intelligence point of view, the context of this part of the talk is related to generative models in artificial intelligence. So the idea of generative models is that you want to build a model which is able to infer the underlying distribution of a certain set of data points, images or text or protein sequences, or can be any kind of data. And then once you train this system, you can use it to generate new samples, new data points, which are statistically compatible in some sense with respect to the original training points. Of course, there are many classes of generative models which are used nowadays. The most famous one is the class of LLMs, like ChatGPT, especially in the last 3-4 years. And I will focus instead on the class of EBMs, so on energy-based models, because I mean they are in a way they are closer to statistical physics in the way we can analyze them, and in the way they have been developed. And also because they can be used for interpretability. Yes, sorry.
So for instance, say you want to generate images, then X is an image, right?
Yes. X is each point will be one image, and you have an empirical distribution of points, which is just the set of images that you have, and you want to train a model based on these training points. Like here. Okay, so this is an example. So here each X here will be one image here. This is the images of the MNIST datasets. I don't know why this does not show up. It's going to be a problem, but okay. MNIST is a dataset of handwritten digits. So they have collected this dataset where people have, people write digits from 0 to 9, and this is basically the most common benchmark in, for classification tasks, for computer vision tasks. This was one of the first big datasets that showed up, and everyone is, in the artificial intelligence community, they always use this as a first, first step, first trial. So in 2 lines, basically the goal of an EBM is to encode the empirical distribution of a set of data points into a probability distribution, which is P of theta here, which has the form of a Boltzmann law, as you can see here, with a given energy function E. This energy will depend on some parameters here encoded in the vector theta. And the goal is that you want to learn, you want to optimize these parameters theta in such a way that this probability distribution is close in a quantitative sense that now we will see to the data. Okay? So from a statistical physics point of view, from an historical point of view, the first developments of EBMs has been in the statistical physics community to solve inverse problems. So the usual way when you study statistical physics in school, well, in school not, but at the university, is that you start from a model was Hamiltonian is known, so what parameters here are known because they describe microscopic interaction between your degrees of freedom, and you want to compute either some macroscopic observables which describes you the equilibrium behavior of the system, or to sample some equilibrium configurations. Here you can see an example which I will recall along the rest of the presentation, which is the two-dimensional Ising ferromagnetic model. In the inverse case, instead, what we want to do is to reverse somehow this arrow. So we want to start from some data, which we assume that they are drawn from a probability distribution that we don't know. And we want to find an effective model in this form, which best describes some of the statistics of this training data. And from an information theoretic point of view, the connection, the way on how to build this kind of systems is given by the maximum entropy principle, which basically gives you at least the functional form of the least bias distribution, or equivalently the maximum entropy one, which satisfies a certain set of constraints on the statistics of the data that you want to fit. Okay? Just to make one example, which is again related to the Ising case. So suppose that your dataset is made of configurations where each degrees of freedom takes only two values. So it's a sort of spin in a classic representation, so plus or minus one. And suppose that you want to find the maximum entropy distribution, which in the simplest non-trivial case fits the first two moments of the data, so the local magnetizations here and the 2-point correlations. The maximum entropy distribution which you can build in this way has the form of a Boltzmann law with an Ising-like Hamiltonian, okay, with external fields and two-body interactions, which then you need to fit so that they best describes these two statistics. Okay, no, this is a problem because I cannot see some. Okay, let me do one thing because some of the images are not visible in the PDF. I don't know why. So let me open. Let me put the presentation actually in. Sorry, no, I can open it here. No. Okay. Sorry, Okay. No. Okay. Sorry. Okay. Yes. Okay. Sorry, no, because also I have a problem with my with the keyboard of this computer, which does not work super well. So it's a bit complicated. Okay. 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 Now we have it. Let me see now if now this works. Okay, now there is some more plots. Okay, yes, sorry. I was here, no? Yes, I was here, yes. So from a practical point of view, I was saying that one of the reasons why EBMs of this kind of architectures here, which I will call in the following as the fully connected Boltzmann machine, which is an architecture in which you have basically two-body interactions at most. From an applicative point of view, this kind of systems has been employed in a variety of applied science fields, like in a context of neuroscience to reconstruct like effective neural connections from firing activity measures. Or I think that one of the most powerful application of this kind of systems was in the context of molecular biology, in particular in the context of the direct coupling analysis techniques, through which you can basically infer the three-dimensional structure of proteins. So the idea is that you can exploit the information encoded in the coevolution and conservation of amino acids in a family of protein sequences which share a common structure and a common function in different living organisms. And you can infer an effective model of this kind here, which is, in this case, it is described by a POTS like Hamiltonian. It's a POTS because you have 20 states, because one is for each amino acid. And with this, basically the idea is the strongest interaction which you will infer. They are a proxy of the real physical interactions between those amino acids who are close to each other when the protein is in its three-dimensional fold. And the development of these techniques also, which was done, this was done at the beginning of the around 2007, 2008, I think. And it has generated a cascade of developments, which then in the last few years has caused also the development of AlphaFold. So, but in a way, some of these developments started with this kind of architectures. Okay. So what I was saying, from an architectural point of view, as I was saying, with the maximum entropy principle, the simplest non-trivial example you can build with which has effective interactions is this kind of architecture here, which has two-body interaction couplings. Of course, and this you can build it when you want to explicitly fit the two-body correlations of your data. Of course, you can say, okay, no, I want to go more than this. I want to go beyond this, and I want to fit higher order correlations of your samples. The point is that if you do it in an explicit way by using the maximum entropy construction, the models that you will get typically have too many parameters. Like the next non-trivial case is when you want to fit three-body correlations. But if you do it through the maxent principle, the model that you will get has all the explicit three-body interactions. And the number of them, which scales as the cubic power of the system size, which is the number of nodes you have, is too much for most of the applications. So yes.
Again, of an image,
yes,
we'll be looking at correlation between pixels. Am I right?
Yes. But you have to think as an image. You have to think that you have to vectorize it. So each image will be a one-dimensional vector of size L squared, where L is the size, of the size of the image, and then you can do this. Yes. The original dataset of the MNIST, no, they have a grayscale intensity from 0 to 150. In this, you can binarize them, and you can binarize them, so black or white, and this typically works well. Yes. Not with the architecture I discussed so far, but because you have to because in that case you have to encode I mean, in that case of the MNIST, the advantage, I mean, the only way to do it is that you have to fit also higher order correlations. You cannot do it only with two body ones. So if you try to learn a model of this kind with the MNIST, it will be very, very bad. Okay? There's no way you can do it. So that's why people have instead said, okay, maybe the solution is to include instead hidden degrees of freedom. So the introduction of hidden degrees of freedom, so latent variables here, is an advantage because now you can show, actually in some cases you can also do the calculations and you can show that they will implicitly account for the presence of all higher order correlations in your samples. Okay, so that's why. So if you want, from a generative point of view, that's why people have started to build more complicated architectures with many hidden layers of degrees of freedom, because you know that in an implicit and complicated way they will account for all the correlations in your data. You can see some examples here. This is, for instance, a convolutional architecture, which is typically used for the dataset of images. And also, which is actually, I mean, I will spend a bit more time on this. This is the simplest example of an architecture of this kind, of an EBM of this kind, with only one layer of hidden degrees of freedom, which is the restricted Boltzmann machine, which has a bipartite structure, which you cannot see here, but you can see it here. I'm sorry that some of the images do not work, I'm sorry. But okay, it's the same one here, in which you have connections. So the parameters of this EBM here are only connections between nodes of one of the two layers with nodes of the other. Okay, and this basically is done because it simplifies a bit the training dynamics. Okay. And this is what I was saying. This is the probability distribution which define this kind of system, and it's simple. So the advantage of the RBM is that on one hand it is more expressive enough to model any kind of complex sets of data. But the point is that it's simple. Also, it's simple enough that you can do calculations. And in particular, one thing that you can do is to extract the effective model from this. So if you imagine to integrate out all the hidden degrees of freedom, you can build up a model of this kind, which you can write with a sum of many high-order interaction couplings. Okay, as you can see here, this has been done also by people in my group at Complutense. Okay, so this was just to give an architecture. Yes, sorry. What, sorry? Tau, yes. In this representation, yes, although here it's called H. I'm sorry, there is a bit of confusion with the notation. Sorry, but so I wrote it, sorry, because this was this is new, sorry. But here the tau are the hidden degrees of freedom, which in principle can take any, I mean, in the architecture that we use, we typically employ all of them to be discrete, okay? So either binary degrees of freedom on both, like spins, or 0, 1 variables, or categorical variables in the case of pots. Okay. So this was just to give an architectural summary of EBMs, just to, I mean, sort of introduction, which is already, okay, a bit late. So just basically 2 slides on the training, because, okay, so far I didn't tell you how to find these parameters here. No? So for any architecture which you can write in this form here, the way to do it by employing a Bayesian perspective, the way to find the best parameters theta is by maximizing the log likelihood function, which you can see here in this form as a function of the parameters. And you typically employ a gradient ascent scheme in which you start from an initial condition on the parameters, and then at each step you move into a direction which is given by the gradient of the log likelihood. okay? And then eventually when this training will converge, so when this gradient here is 0, you can interpret the maximum likelihood point as if it's satisfying a set of moment matching conditions between all those observables, which you can write in this form here. So this will be the observables that you will fit for between your model with the parameters computed at the maximum likelihood point, and the same observables computed empirically with your data. Okay, so now the point is that basically from a computational point of view, all the problems related to the training dynamics of EBMs come from this term here of the gradient. So the gradient and the log likelihood, you can write it in a generic form in this way as the sum of these two terms. And the problem is that while this first term here is easy to compute because it's just a set of local empirical means, which you can compute it based on an amount of samples that you have. In this case, this is a sort of equilibrium expectation, which would require you to compute it, I mean, in an exact way, would require you to sum up over all the exponential amount of configurations that you have. This, of course, is unfeasible. So what typically people do is to use it to estimate it through some sampling. Okay. Sampling means that every time you need to initialize a certain set of configurations, which are called chains. You need to evolve them in such a way, so by satisfying detailed balance like conditions such that if you evolve them for a long enough time, these chains, the statistics of these chains will converge to the equilibrium target distribution, which is this P of theta here. And then once you reach this point, you can estimate this gradient here. And the point is that, okay, this is very complicated, but because there are many problems related to this sampling here. One of the problems that you have is that typically the thermalization time, so the time required to reach this sort of equilibrium stationary state here, increases during the training dynamics. So it is more and more complicated. So there has been in the last few years, in the last 10, 15 years, there has been a lot of effort in trying to do this sampling in an efficient on one hand, but also in a controlled way by exploiting, for instance, clever initialization of these chains or advanced sampling techniques, okay, like parallel tempering. Don't discuss. I will go into the details of this, but the point is that now, at least for some architectures like restricted Boltzmann machines, now we have somehow a good amount of control on how to train them well. Because this was, I mean, from an historical point of view, RBMs were invented at the end of the 80s, but then they were somehow they fell into disgrace because the training was uncontrolled and people did not know how to train them well and did not know how to interpret the results. So now this somehow also thanks to people in my former group, this has been a bit more solved, and so now we can control a bit more what is going on. Also, just to say somehow my contributions in this kind of field. So we did two theoretical papers which look one looks at this term of the gradient here and analyzes what happens instead when you use a sampling time which is much shorter than the thermalization time of the model, and this is related to a sort of out of equilibrium training strategy, which in principle you can exploit to some extent if you want to generate only good quality samples and not to learn a good model. And also we investigated in a more recent work, we investigated what happens instead when you look at this term of the gradient here, which is, this is computationally easy to compute, but here is, this is where the amount of training points and the structure of the data can impact the quality of your training. And so this is a work which is related to the problem of overfitting. And well, I won't discuss about this because I want to go on, because because maybe then there is not much time to finish. How much time do I have? I don't know when I started. Oh, I don't remember when I started. I have half an hour. Okay, it's here. Sorry. Okay, sorry. That was okay. Sorry. Okay, this was just basically a sort of theoretical analysis, which is related to this paper here, in which you can basically show that along the training dynamics, when you don't have a sufficient amount of samples, there are specific times during your training, which if you were able to stop there, if you were able to know what these times are, these sort of early stopping times, you will get a better model than the one that you will get at the fixed point, so at the maximum likelihood point. And this is because the idea in one line is that in the first part of the training, you learn the good information which is contained in your training data, and then after this point, you start to overfit. Okay, you start to fit the noise in these samples, and we did a theoretical analysis of this in a very simple architecture, and we are trying to develop a sort of generic way, for instance, using random matrix theory to try to estimate where this point here, because of course this is a synthetic experiment where you already know the ground truth. So of course this is, sort of cheating, because here you know when you can stop, but in a practical case, of course, you don't know. So it would be nice to estimate it, and there should be ways to do it. But okay, I will not get into the details of, because it's another part of this story. So just to tell you some of the things that I will like to do, that I would like to do with the time I have here. But actually, because like this one here could stimulate some discussion with the neuroscience group. So as I said, okay, now we are in the case of restricted Boltzmann machines, we know how to train the model well. So we know how to we know that the model that we can infer is good. It does not overfit and things like that. So now we wanted to apply these kind of architectures to some sets of data. So in the context of neuroscience, there is this these experiments with neuropixel probes, where basically they put electrodes in the visual cortex, not only actually of the brain of mice, and the mice has to do some visual tasks, so it receives a certain amount of visual stimuli which change in time, and then they have to do some action when the stimulus changes. Okay. So there is this data sets in which you can record the firing time of each neuron, which is in this, which is connected with this neuropixel probes, and you can, in principle, the idea was to, okay, we want to learn something about this set of data. There is two assumptions here which we do, which are very crude from a neuroscience point of view. So I'm sorry for that, but one of them is that we discretize the firing activity of neurons to be either 0 or 1. Okay, so this is a bit crude, but the idea is that it can still, you can still learn if there is some collective activity pattern. And also we assume that this is the typical assumption when you do this kind of equilibrium-like inference, that you assume that the samples are independent on the others, which of course is not true because this is a time series. So you only use the information due to static correlations. Okay. So from a generative point of view, this is okay. I'm sorry with the, okay. This was to show, which is not very clear though from this. Maybe I can, I'm sorry, this is the first time that happens. But if you allow me to get here, here, yes. You can see, maybe, okay, you can see, sorry, now we'll get again to full screen. You can see that we can learn a good model with the minimum amount of hidden neurons that you need, so you do not overfit. And I mean, the model that we can learn here, there's a population of around 1,500 neurons, and we can learn this kind of data with a recited Boltzmann machine, so that it reproduces quite well the statistics of your sample. So from this point of view, we know how to train things well. So we are able to reproduce this statistics in a reliable way. And what we wanted to do is now to do some to extract the effective coupling, which is here. So the idea is that, as I told you, with the RBM architectures, one thing that you can do is to extract an effective model which is composed by a sum of many high order interaction terms. Yes, Raul.
Data from neurons that are like all of the same type, like all the neurons that you consider like it's that or you're bunching together, like that's what it is.
I think that you take both of them into account, I will say. I'm not sure, but yeah, I think so. There is not a selection on this type, I think. Also, they belong to different regions of the brain, which you know it from the data. So the idea is that you can extract, in this case, of sort of effective two-body interactions, which are showed here. This is just an histogram here. And you can, so the idea of this point is, okay, since I'm not into the neuroscience field, I mean, it will be nice to, have a discussion with the people in the neuroscience group to make sense of this. I mean, to see if this somehow has some interest, and if we can we can infer something which is related to the plasticity of the brain, because so there are two settings in which these experiments can be done. One in which the mouse sees the visual input for the first time, and then they do another experiment where they do again with the same kind of stimulus, but the mouse already knows it. Okay, so the idea will be to see if there is some structural changes at least in the effective model that you can build, which you can infer from here. Okay, this will be related to this kind of plots where I'm plotting a sort of Frobenius norm, but normalized on the neurons which belong to two brain regions. Yes, over there.
The couples, are you using a restrict Boltzmann machine with hidden layer?
Yes.
Then you get the...
So then you can compute this once you basically integrate out the hidden degrees of freedom. Yes, this can be computed once the model is trained. Okay, so once you have maybe let me go back to this. So when you train it, you optimize these weights. Okay, the weights which connect neurons from the visible layer and the hidden one. Okay, then once you train it, these are now you don't change them anymore. You integrate out the hidden degrees of freedom. What you get here is a Hamiltonian with many body interactions, which you can compute. You can compute them Yes. In terms of these weights, of the hidden node being because you have integrated them now, but with respect to the weights, yes. Of course, I mean, an exact computation is exponential, but you can compute them well by using some numerical integration. So this, I mean, can be used. Yes, also for body and more. I mean, up to. Huh? At the beginning, no, because I mean, typically you start with these weights which are very, very small. Here. Which one? Here? Here? Back, I don't know where. Yes, okay, this was way back. So let me, okay, here. Here.
That's all you.
Yes. No. But okay, but you have to, okay. So these two body interactions, this W here are between one visible node and a hidden one. Then when you integrate this out, what you will be left with is only this set of hidden visible degrees of freedom, and you can compute all the one body, two body, three body interactions, and each of them will be a function of these weights. Okay, and on the external fields. Okay, but yes. This is the idea. Actually, depending on the kind of architecture that you have, there's some papers where they have computed. So I mean, there is all the formulas that you can use. This is done. Sorry, I got lost. No, I didn't get lost. Okay, so this was one part of the story. Okay, more data-driven, and I hope to interact more with the neuroscience guys on this. Then there is another project which this is a bit of an old idea, which somehow tries to go beyond the standard maximization of the likelihood to include some information about the graph being sparse. So suppose that you want to infer, in the simplest case, Hamiltonian with two body couplings, but suppose that you know that the graph is sparse. Maybe you can use this prior information, and the idea, this is just an example to try to explain what I mean by this. This is another example of a reconstruction of a 2D Ising model from equilibrium configurations which are drawn from another Ising model. So you can see that, okay, of course, the quality of the reconstruction will depend on the amount of samples that you use. Okay, so if you have many more, I mean, if you have a sufficient amount of samples, then you will reconstruct it well. So here you can see a comparison between the true coupling matrix, which is the bottom left one, and the inferred one, which is the top right one. Okay. Of course, when you start to decrease the amount of samples, the quality of the reconstruction will get worse. Okay. You can see it more quantified here when I'm plotting the rock curves for the reconstruction of these interactions. So the idea of doing the one, I mean, there are many ways of doing this, for instance, by using regularization penalties, but the problem of regularization is that you have to fine-tune the regularization strength, which typically does not have a clear physical interpretation. One idea which dates back to my PhD time, and we are trying to revisit it because now we have found a way to do it more efficiently, is to simplify a bit the problem by simplifying the likelihood. So suppose that you have found a point suppose that you have found the maximum likelihood point. So when you don't have any prior information that the graph in this case is sparse. Then you can look into the surroundings of the maximum likelihood point. So you can compute fluctuations, in particular quadratic fluctuations around the maximum likelihood point. And on top of that, then you can look for a sparse. So in the surroundings of this point, you can look and you can look for a configuration of parameters such that the graph is sparse. Okay. There's a way to do this by using, for instance, this prior here, which basically this is called spike and slab, which enforces a finite fraction of parameters to be 0. So the graph you will actually infer here is sparse. Okay, and of course, if you introduce this prior here, things will get once again interactable from an analytic point of view, because the posterior that you will get from the expanded likelihood up to the second order plus this term here for all the parameters is this cannot be, I mean, this cannot be analytically integrated, but you can use some approximation schemes, and in particular this one here, which has to do with this expectation propagation algorithm that has been invented at the beginning of the 2000s, and this can be done. I'm saying that this can be done because we already have some results on this. So this is a very simple example on a Gaussian model. So the idea is that you want to infer a probability distribution of this type with a J, which is the inverse covariance matrix of the Gaussian, which is sparse. In this case, in particular, I think it was drawn from a random graph ensemble. So it's like a Poissonian graph, okay? With a certain mean connectivity, which I don't remember now, but okay. So you can see that I mean, if you apply this sort of expectation propagation scheme, which I will not go into the details of, but this can be done, and you can already see that there is some improvements. So I'm plotting you here the rock of the area, sorry, under the rock curve for the reconstruction of these interactions, and you can see that there is, non-negligible improvement with respect to the maximum likelihood point. And okay, this is so far it's a toy example, so maybe it's not very interesting. The context in which I would like to apply this kind of stuff is in the context of structural prediction of molecules of RNA, for which the contact prediction problem, so for the point of view of from the point of view of proteins, it has been solved. Okay, but from the point of view instead of molecules of RNA, it's still a bit more complicated. It's still an open challenge, mostly because they are typically less sequenced data for RNA, and also because RNA molecules typically undergo many more conformational changes between one organism and the other. So it's a bit more complicated to estimate the true three-dimensional interactions. In particular, the ones which define, so the ones which define the tertiary structure of these molecules. So I would like to apply this kind of procedure in this context here, because I think that we can have some improvements. Okay, so the last part of the talk, which I don't have time to deal, so I'm sorry. Okay, the last part of the talk deals more with the last 2 words of this very complicated title, which I chose, and for which I'm sorry, but has to do with this sort of cooperative learning. So it's another, this is a bit more theoretical, and it's a topic which is more niche, if you want, in the disordered system community. Gianpaolo already knows where I'm going. So, okay, so so the point is that from a theoretical point of view, one of the questions which you can ask is under which condition the amount of information that you have of a given inference problem is enough or not enough to solve it. Okay, just to make one cartoonish example, if I give you this, if I generate this signal, which is very clean, which is 0, and then it has one spike here at the center. I corrupt it through some noise, and then I ask you to locate where this spike is. No? Then of course, I mean, if the noise is low, okay, say the spike is here. No? If instead the noise is too high, you cannot anymore see where the original spike was. This is just to make the point. Okay. So from a statistical physics point of view, there is a framework through which you can study these inference problems, which is the so-called teacher-student or planted setup, in which you start by generating a planted configurations, which is your ground truth, which is this X star here. Then you generate some data according to some probabilistic model, which is given here. Then you take the data which have been generated conditioned to this ground truth, and then you give the data to a student, and you ask it to retrieve the ground truth. Okay, very simple. The typical case is that when you go to high dimensions, the thresholds which separate regimes where the inference is possible or not, depending on the amount of data you have, for instance, they become sharp, and they can be analyzed in terms of phase transitions. Okay, so there is a whole bunch of literature, particularly in the spin glass community, which studies this kind of problems. One example, just to make an example, which maybe you are familiar with, is the planted graph coloring, in which you want to color with Q. I mean, you are given a graph and a certain set of Q of colors, and you want to color the node of this graph such that if you take any edge of this graph, the nodes which are connected by this edge, they have to have different colors. Okay, this is a well-known inference problem which can be studied within this framework here, for which you can compute these phase transitions. Okay, and the picture that you typically get is that, I mean, in one class of inference problems is this kind of, you have these three regimes, depending on one, possibly more parameter, which plays the role of a signal to noise parameter. So they quantify the amount of information that you have about the inference problem that you want to solve. The typical picture in this class that you get is that you have either an impossible phase from a thermodynamic point of view, where you basically don't have enough information to solve to find the ground truth. Then there is an easy phase in which you have a sufficient amount of information for which at least one class of algorithms in an optimal setup, they will work. They will find this ground truth from this point onwards. And then in the middle, there is this hard phase, which is a bit more complicated to study, in which the inference from a thermodynamic point of view should be possible. But in practice, there is a cluster of suboptimal solutions which do not allow you to find the ground truth. And this is typically studied within the spin glass theory, because there is a ergodicity breaking phenomena, which have been studied by using replica symmetry breaking theories and things like that. So one more ingredient, and then I think I will be over, is that instead, if you can also use algorithms to solve this kind of inference problems, which are based on optimization schemes, for instance, based on some sampling, like simulated annealing. And the problem is that these algorithms here, they are typically suboptimal in the sense that there is an extended region within this green phase here, in which they should find the ground truth too, because this is the green phase, the easy one. But in practice, they don't find it, because they get stuck into some configurations which are called metastable states, in which the dynamics gets trapped. Okay, and the point is, okay, this is the example that I was telling you in the case of the planted graph coloring, and there is a sort of conjecture which has been verified. I mean, numerically verified, at least in this case here, in which if you, instead of optimizing this Hamiltonian here, which is the one that you would use in the case of the planted graph coloring case, if you replicate it a certain amount y of times and you add the sort of ferromagnetic interaction between these replicas, the dynamics of optimization of a simulated annealing-like scheme on this Hamiltonian here does not get trapped in these metastable states, but finds the ground truth. Okay, so there is a whole bunch of theory going on here, which we have also tried to try to investigate, and we did a work on that in which we analyzed the thermodynamic properties of this sort of extended ensemble. In this case, by focusing on a model of a very simple neural network, which is the perceptor, but with the spin-like weight. And we have found a sort of, we have analyzed the thermodynamic properties of this extended ensemble, in which you have many replicas of this system, which are coupled by this sort of ferromagnetic interaction. And okay, I will not go into the details because I don't have time, but the idea in this part of the project that I wrote, was to go a bit beyond this and to study more in details what's going on from a theoretical point of view, by looking at the dynamics, for instance, by using dynamical mean field theory, and to check if this sort of conjecture is actually true, and how, if this can be studied in more examples of inference problems that have this kind of phenomenology. So the idea in 2 lines is that if you take more students and you couple them in this way, they need a bit less of information to find the ground truth with respect to one single. And one of the models that we were trying to think about is the one spherical model, which is the mixed spherical p-spin model with a spike. Gianpaolo here knows more than this more than anyone else. I think he worked on this during his PhD. So we wanted to study this. Also, there is some numerical experiments, like there is some people at BIFI in Zaragoza, like Alfonso Tarancon, maybe you know him, who have studied this kind. From a numerical point of view, there is some experiments which you can do, in which you basically study collective dynamics of learning, in which you have many students, like on a 2-dimensional grid, and they can copy from each other. So they can use they can update their states. In this case, their parameters based on the response of your neighbors. And also this setting in principle can be extended to a context which in artificial intelligence is called federated learning, in which you have many students, but many units which have, in which each unit has a different subset of training data. So the idea will be to investigate a bit more this this kind of stuff. And with this I conclude, because I think I'm largely do. Just okay. So the whole point of this, was to give a overview of some of the things that I have done. If someone is interested into any of these things. Actually, these three asterisks should be also here. So I don't know why they are not, but here they are here. Okay, so these are the typical things that I will try to think about in the months here in this in the next few months. Of course, I'm not pretending on doing all these things in 1 year, but I mean the point is to give some inputs for some future discussions and or collaboration. Okay. So with this, you will geographically you will find me at the other campus in Park Bit, but I can come here whenever you want. Okay. With this, thank you. So,
Thank you for such a comprehensive talk. Many questions or comments? Anyone?
Regarding the gradient descent calculation with Monte Carlo
which one?
in the energy-based model.
Okay, in the first one.
So if the landscape is complex, how do you do? I mean,
no,
your
if
hypothesis is that you have a convex landscape.
No. I mean, this in the case of restricted Boltzmann machine, it is not convex. So the likelihood is not convex. So in principle, we have many
To the Monte Carlo to evaluate the gradient. If it's complex, the landscape.
That's why. But one other thing which I didn't say is that you can have like mod collapse. Like that, your gradient, like your configurations will visit only one of the clusters of your.
So you develop a model that.
No, but this can be solved. I mean, if you do like a parallel tempering, you can jump more between the.
Okay. So you need to do something.
Yeah. Exactly. I mean, if yes, that's what I was saying. What I didn't say, but. When I said that there has been a lot of effort in how to try to improve this gradient here, there is a lot. There's many papers on how to do this in a more reliable way. Also,
I mean, if the number of minima is exponential, for example, then.
Okay, but this is okay. If you for a finite size,
the case of the spherical model, for example.
No, okay, but you have to yes, but we are. In this case, we only look at things that are finite size, and typically, what you can assume is that for the part of the configuration space which is related to the first principal components of your data. The barriers that you have, they do not grow exponentially with the system size. One thing that you can do, for instance, in this case, is to, like, at least in the case of RBMs, there is a way to initialize the training in such a way that if you have two clusters of the data which are not connected, you can learn a machine which was projection on those two directions gives you exactly the distribution of points in those two clusters. Okay, but this is a low-dimensional, low-rank sort of approximation. But yeah.
Questions? If not, okay, we thank Ivan again.
Can I?
Devo organizzare